we always think of Lake Tahoe as the be-all and the end-all, but really it's just the beginning of a much bigger watershed. There's Tahoe, we have 63 streams coming into it, and then via the Truckee River, it goes on down and it feeds a whole system, ending in Pyramid Lake, which you've got water supply for Reno, you've got an incredible trout fishery, you've got water being diverted to a whole different system. That was, I think, the first federally approved irrigation district in the country, that water diversion. Anyway, it's important to know that it doesn't just begin and end at Tahoe. What happens here is important downstream as well. So, if I was alone at Tahoe, the world has ended, the world as we know it has ended. And I think finally I can do some science without having to write reports and deal with people. And what would be the one instrument, other than the Secchi disk? I presume you all know what a Secchi disk is. What one instrument would I have? And actually, if you were at Tahoe all by yourself and were interested in the lake, what instrument would you want to have? Just thermometer, microscope, water filters. Well, that's not an instrument, that's a tool. It's a difference. Well, anyway, Heather's heard this before. So it's a thermometer. And why? Why a thermometer? Because pretty much everything that happens in a lake has temperature associated with it. Not just the heat part of temperature, but the way temperature changes the motions of water. So we all know about oceanography. Oceanography is a very exciting field, big boats, big budgets, all of that. But if the ocean was the same temperature and the same salinity top to bottom, where it was just a big ocean basin full of the same water, it would be a very dull, uninteresting science. All the motions that happen, and those motions dictate what lives there, what things you would see with a microscope, for example, all depend on the temperature and how it changes motions in the water. So what we're seeing now is a typical temperature distribution for Lake Tahoe. I don't even know what year this was, but it doesn't change much. So these are the months of the year. I mean, January and February aren't there, but they're just more of that blue color. But what happens is at the beginning of the year, and this goes back to January, we have what we call the unstratified period. Now, when you start using words like unstratified, people's eyes start rolling. I can see your eyes, like unstratified. And we're only on the third slide. He's using words like this. What that means is, yeah, this is all just pretty much the same water, same temperature. It's free to mix, top to bottom. But once we hit spring and summer, it's stratified, meaning the top of the water warms up. Why only the top? Because sunlight shines through, it doesn't go all the way to the bottom, it gets progressively absorbed, and so it's only that top part. Depths are shown in meters there, but it's only, well, actually, light will penetrate in Tahoe down to about 300 feet. So actually there is, you can see, there is some measurable light getting down to the bottom of this graph, but most of it's up there in the top 50 to 100 feet. As I said, the actual temperature, the heat part, is secondary. When water is warm, it's light. So you can think of the whole summer period, light water floating, and the red, yellow water floating on top of this dense bottom water. So if you ever go to a lake or a beach with a beach ball, beach ball full of air, and you try to push it under the water and let go, it springs back and hits you in the face. It's the same with this. If you take some of that light water at the top and we're able to push it down, it would spring back. It doesn't want to mix. It wants to be, it belongs with that light, warm water at the top. So the temperature creates this resistance to mixing. So this period, lots of mixing. Here, an absence of mixing. Okay, so we don't have simple thermometers like the one I showed. We measure temperature in a bunch of different ways. We have instruments like this that measure temperature as that instrument falls through the water. It falls through the water at about a foot per second, and 8 times per second, it's measuring temperature, along with a whole lot of other things. This is one of the buoys we have out on the lake. Below that, there's a string of temperature measuring instruments that record the near surface temperatures. It also has, on the end of this arm, a measurement of the radiation emissions from the surface of the lake, telling us what those temperatures are. In the same way, that's the same instrument that is on satellites. So when you see these pictures of El Nino, this warm current going across the Pacific, it's basically made with the same thermal infrared instrument that's there. And we have similar temperature instruments in the near shore of the lake. Our newest instrument, and this one's so new we don't have data from it yet. Actually, I asked our researcher who's working on this, I texted him this morning to say, sorry I'm leaving it a bit late, but I'm giving a talk this afternoon. Can you send me some data? And he sent me a photo back of him hiking and somewhere in Utah. There you go. This is very cool. Essentially, it's a wave-driven profiler. So this is what it looks like if you were to go out there. There's a buoy. This is off the west shore. This instrument is underneath, and it's on a wire. As waves pass, whether it's wind waves or wakes from boats, it has a little cog mechanism, and it drives down 300 feet. Gets to that depth, it lets go, it disengages, and then it rises up, and then it's taking temperature measurements and other measurements on its way up. And you say, well, is that different than that other instrument that they lower from the boat? It is in one fundamental way. That is, the people on the boat refuse to go out day and night, every day of the year, and take those measurements. If they would, Mike, we wouldn't have had to spend money on this. But this way, if there's a storm, it's measuring. It's measuring more frequently if it's a storm and it's windy. There's more energy to drive it down. So we're really excited about the data we're planning to get from this. Okay, temperature stratification that forms during the spring and persists through the summer and fall prevents water from moving very far vertically. Okay, so I think this is Ward Creek. It enters the lake. Here's the lake. There's Ward Creek. Ward Creek probably has a different temperature than the lake. But we know the lake's temperature varies as we go down. We also know that Ward Creek's temperature varies something like, in Fahrenheit, about 12 degrees Fahrenheit every day during the snowmelt season. So you've got this whole, where is this water going to go? Is it lighter than the surface? Is it denser than the surface? Will it plunge down? That's actually, we've just concluded an experiment looking at just that question. Again, the data from that is still being processed. What I can tell you, though, is if we were to just integrate, we average all the water from Ward Creek and see where it goes horizontally in the lake. So just the surface water. And most of it does stay at the surface being the top 100 feet. Where does that go in the lake? And this is an image of that. So this is water going, this is about, I think this is about a 2-week simulation. So this is as if we're putting red dye into Ward Creek constantly, and this is where that dye is going. Now, don't think that people like Mike and the other folks who are out on the lake are running around taking these measurements continually. They're not. They can't. That's impossible. This is the product of a model, a computer model, a computer simulation that we trust because it's being calibrated and validated using the data they do collect and the meteorological data, the weather data that they collect. So essentially, after what it is, a month, the whole water, all of the lake, you see different colors. It's no longer that dark blue. Not multiply that by 63. I mean, there are 63 streams. Ward Creek's one of the largest ones, but you can see streams do have an impact on the surface, and they're bringing in nutrients and they're bringing in particles. So understanding where they're going is important. And I'm sure that was a question you all had. Laying awake last night wondering, I wonder where all that stream water goes. Okay, this is something that's, it got this name flipping. I think I was trying to be clever one day, and I was doing I had to do a presentation for another group, and I said, I'm going to use the F word throughout this. And so flipping was the first F word I used. And so what's flipping? We generally call it turnover. So this is when the lake finally does mix vertically. During the summer, it doesn't mix. So, but every winter, the lake does mix down to some extent. And so it does very much. Okay. Let me just is the middle. It's rarely the wind or something like that. So let me explain the size of the lake. About 40 degrees above. This is a little bit it's cooler. A little bit of snow the other day. It snowed. It's cooling, and now there's mixing going down further because it's more uniform down there. But at night it's mixing maybe halfway down. It's 45 degrees at the bottom to 42. Usually, so in late February, some years it will mix all the way to the bottom. And that's when we have what we refer to as the lake flipping. It's now freely mixing top to bottom. Okay, so this is data from 2023. That was the last time the lake flipped all the way. And so what that red is the temperature of the surface water from this buoy. And basically at this point, late February, when it passed, this blue line is the bottom temperature. At this point, whatever date this is, 28th of February, I think, it starts to flip. And then the surface temperature keeps getting colder and colder. This shows, get your head around something first. This is showing the depth of the lake from the surface to the bottom, like down to 450 meters anyway. And these are to the way to the bottom. They are years when it flipped. All the other ones, the thin gray lines, that's how far it mixed. That's your temperature. The circles are the years when it did flip, and most of those circles a certain temperature there. Okay, interesting thing about Tahoe. This graph should be, this is depth, and this is showing just the distribution of how many years it mixed through depth. And there's a gap. It never mixes down to something like 40. Once it passes 3 feet, it just can't stop itself. Slightest change. Okay, the lake is beautiful. it's clear. Surface at the top, the bottom is perfectly clear. So every time, every winter, when the lake mixes down, it's bringing up some of this clean, pure bottom water, diluting the surface. So the year when it last flipped, 2023, the Secchi depth was 115 feet, which is really good. But 2 weeks before that happened, it was only, it was a lot less than that, 33 feet less than that. The other thing it does is it brings oxygen to the bottom of the lake. Lots of oxygen in the surface water. At the bottom of the lake, oxygen's always decreasing. It's always getting less and less. And why? Because everything in the lake, all the algae, all the zooplankton, the little microscopic creatures, the fish, they eventually die, fall to the bottom, they decompose. Decomposition uses oxygen. So if you don't have any mixing all the way to the bottom, eventually you'll run out of oxygen at the bottom. That's bad, as we'll see in a minute. 5 minutes. Okay, that's good. Freezing, second F. Does Lake Tahoe ever freeze? So this was taken, again, 2023 was a pretty exciting year. This was Emerald Bay on February 1, 2023. You can just sort of see that it's like a really good martini. It's just got that crust of ice on top. For those of you who are over 21. This was March 15th. That's Emerald Bay. Frozen over, not frozen solid. It's just on the surface. Ice there, covered in snow. The rest of the lake didn't freeze. That sort of answers that question. You know, Lake Tahoe never freezes. And I say never cautiously because it's never frozen since people have been collecting data on it. Primarily because it's just too deep. Winter isn't long enough to remove enough temperature from the lake. So the surface has to reach 39.2, and it's never reached that. But if it did freeze, it would be great, because lakes that have an ice cover, when that ice cover breaks up in the spring, they actually have another deep mixing event. So we would have flipping twice a year if we had an ice cover, but we don't. So let's not go down that rabbit hole. Festering, third F. So again, this was 2022, the year before 2023. And we had how many of you were around 2022 at the lake? Well, you may remember, it was pretty horrible, especially down on the South Shore. So this was a photo down at the South Shore. So around the shoreline of Lake Tahoe, we have algae. This is sort of very different than what's happening in the middle of the lake, where it's so clear. And by middle of the lake, I mean everything more than a few hundred meters offshore. So the whole shoreline, you can see these patches of very shallow water with that sort of brown-green algae. The last few years, we've developed an ability to use helicopters and drones, and in the next few years, hopefully satellites as well, to image this whole shoreline to see where these algae are, because it isn't the same every year. 2022 was really bad. The following year wasn't nearly as bad. So this is what it looks like. This is around Tahoe City, just south of the Truckee River outlet. So this is, again, the most extensive periphyton blooms. So periphyton, they're algae that have to attach to something. You see them on rocks there at the bottom of the lake. So they were just huge expanses at that time. Meanwhile, at the other end of the lake, we had something that was relatively new, and this is called metaphyton. So, and I mean, these are pictures that we don't normally associate with Lake Tahoe. Lake Tahoe has, golden beaches and you can see the bottom, it's clear. It was not like this in 2022. It had this metaphyton. Unlike the periphyton, it doesn't have to attach to anything, but it's very filamentous. So it sort of sticks together. And if you're in the water, it would be there. If you just kick it with your foot, it would sort of disintegrate into 1,000 pieces. But then when it washes ashore in these mats, this is what you have. So what's causing it? We didn't get this 10 years ago, 15 years ago. What we think, and I think we're sort of at the 98% sort of belief level now, is that this is caused by an introduced species, the Asian clam, which showed up about 20 years ago. And why it's there is that Asian clams, essentially, they're filter feeders. They bring in water, they filter out the algae that they're going to grow with, they use it, and then they excrete. Their excretions, because they've concentrated all this algae, are about 10 times higher in nitrogen and phosphorus. So what they're really doing is fertilizing the bottom of the lake. What can be done about it? Well, we did an experiment a few years ago looking at harvesting, and that actually does have some potential, but it's still at a very early stage. Many years before that, we came up with a way of putting rubber mats down on the bottom of the lake. And that works at the sort of 98%, 99% level, but it's expensive. You got to have divers. It's a large area. You got to put it down. You got to remove it. And because it's only 98% effective, in 10 years, they're back there again. So it's kind of like painting a bridge. You start, and by the time you get to the end, you're ready to begin again. So that requires money and a commitment to do that. These things seem to be worse when lake levels are low, water is warm. So that was the case in 2022. Where are the Asian clams? Well, they're all along the South Shore, basically. A large area of the lake. On the East Shore, they exist in pockets going up the East Shore. They're in Sand Harbor, for example. They're in relatively low numbers there, maybe 100, maximum of 100 per square meter. But every year they seem to be getting more. They're starting to see this metaphyton, where they have them. So on the South Shore, sometimes they're like 2,000 a square meter. I mean, so on 2,000 clams buried in the sand of that area. All right. Epic clarity. I couldn't think of an F word for clarity. So Tahoe has epic clarity. It's known the world over for its clarity. And this is the famous graph. Each of those white circles represents the average over the whole year of about 25 measurements that are taken, summer and winter. I was going to say day and night, but we don't do them at night. So just daytime, usually close to noon. And I mean, 0 is at the top. And so back here in the 60s, it was 30 meters, 100 feet. And it has been declining for most of that period. There are periods of time for a few years where it improves, but then the overall trend is one of no improvement. This last year, the average was 62.3 feet. So that's the reading for the last year, which is not great, not epic. Sometimes we lose, personal opinion now, sometimes we lose perspective. Most lakes in the world would love to have a problem of only having 62 feet of clarity. I mean, that's amazing. But we used to have 100 feet of clarity. And I think there's a commitment, more than a hope, there's a commitment that we should be able to manage what we're doing here to get back to that, or at least get closer to that. And I think that is, what's driving a lot of the belief in restoration, is to be able to do that. And you could say, well, Tahoe's one lake. What's the big deal? Big deal is that people watch Lake Tahoe. And if we don't manage to do it there, there isn't a whole lot of hope for all these other lakes that don't have the attention or the resources that Tahoe has. So let's get back to our epic clarity. So sort of building on that last point, there are a lot of lakes in the world. So the largest lakes, over 50 square kilometer, there are 3,000 of those. The smaller lakes, less than 0.1 of a square kilometer, it's 250,000 of those. That's just North America. So, and I sort of touched on some of the measurements we do here. None of these lakes are going to have anything like the sort of measurements we have. Not the vast majority, over 90%, will not have any measurements at all. So what can we do as lake scientists or people concerned about the health of lakes everywhere? How can we address that problem? So I guess the way I would sort of broach that, how am I going on time? All right. Is to say, well, what can we learn from Lake Tahoe that applies to all these other lakes? Can we somehow leverage, what we've done here, what others have done here, the resources that have been made available here to help all those other lakes? So the physical processes that we've just touched on a little bit, they're pretty much the same everywhere. Gravity is gravity. Density difference is density difference. But there are lots of local things that change. The shape of the lake, the depth of the lake, their particular meteorology, the longer term climate, what happens in the watershed. All those things change an individual's lake, the individual lake. But the physics of it stay the same. So physics, as all of you know from your experiences in high school and college, is easy, right? Believe it or not, the hard part is the biology. It really is. Just think of Lake Tahoe. There are hundreds of algae, hundreds of types of algae in Lake Tahoe, and dozens of zooplankton. Every year, a different one or a different group of them are in ascendance. Why is that happening? Well, we can explain that after the fact, or we can try to explain it, but we don't know. It's hard to predict how these things happen. The physics, we can predict with great certainty. The biology is harder, but people are getting better at it. So, but if we understand the physical processes and we have some understanding of the biology and the chemistry, maybe we can use tools like models to make estimates of what's happening in these unmeasured lakes or undermeasured lakes. Okay, so we use computer models to describe these processes. They help us understand things and make predictions. Okay, so this cartoon, it sort of really looks complicated. Just a cross-section of a lake. We'll see, for example, this is a stream coming in, and this is showing the water coming down, but which has a different density than the lake. But at some point, when it's at the same density, it flows out at that same level. Different time of year, it may go down to the bottom. What causes circulations in the lake? Big gyres, physics, we have good estimates of how that happens and the amount of mixing. With that, we can predict pretty well the temperature stratification, which controls the amount of mixing. And this is the oxygen stratification, but that relies a little bit on these boxes. So each of those boxes are also little models, but models that have much bigger fudge factors because we don't understand it. And I'm not just saying TERC doesn't understand it. I'm saying scientists everywhere have less understanding, less confidence of that than in the physics. These are tough problems. So we've spent a lot of time building such models of different kinds and using them in different places. So I want to give you an example of a very different lake than Lake Tahoe. All right, so this is Clear Lake. Anybody been to Clear Lake? Oh yeah. Okay, well good. Its history is interesting. In the 20s and 30s and 40s, this was Lake Tahoe. Well, not really. It was as popular as Lake Tahoe. People from San Francisco went to Clear Lake. All the Hollywood stars of their day had ranches at Clear Lake. It was beautiful. It's an incredible fishery. So people used to go fishing. Unfortunately, well, several things happened. One, Clear Lake started to degrade. And then they also put I-80 through the Tahoe. So suddenly more people started to go to Tahoe. And so Clear Lake has declined. You get a sense here of part of the problems there. These are just cyanobacterial, so algal blooms, potentially toxic algal blooms, just swirling around there. Okay, so this is what Clear Lake looks like. It's all those symbols are a little bit big, but they represent places where we take measurements. We've been taking measurements there for the last 6 years. These lines represent depth contours. So Tahoe, as you know, is 1,641 feet deep, something like that. Clear Lake, at its deepest point, is about 50 feet deep. So suddenly, this is a very different lake. I mean, latitude-wise, they're not all that different. Altitude-wise, yeah, they are different, but this is a shallow lake. As I said before, Lake Tahoe mixes all the way to the bottom, maybe every 4 or 5 years. Other years it mixes down maybe 1,000 feet. This lake is 50 feet deep. So what happens here is that it mixes even in the summer. So shallow, it stratifies, gets warm on top, but then you get a windy few days and it mixes to the bottom. So this is these are graphs that engineers love. I love these graphs. Most of you probably don't love it as much as I do. This top graph represents the measured temperatures in the lake. So we're going from April, say, through to March. The different colors represent different temperatures. The red is the warmer temperatures, the blue are the cooler temperatures. Important thing to notice there is during this red period when it's warmest, there are contour lines there in the red. You see those lines? That represents that it's stratified. It's even warmer at the top than at the bottom. And we know when that happens, mixing is suppressed. This graph represents the measured oxygen. And when we have strong stratification, very quickly, oxygen at the bottom of this lake disappears. In a matter of a week, it goes from 7 or 8 micrograms or milligrams per liter to 0. So low oxygen, low oxygen, low oxygen, low. So all through the summer, the growing season for algae, oxygen is disappearing. So you say, oh, that's really bad for the fish. It is, but fish are smart. They stay away from the bottom. What's not so good is when oxygen is depleted, chemistry changes. Phosphorus comes out of is released from the bottom of the lake. At Clear Lake, there's also a Superfund site, a former mercury mine. So there's mercury here, so something called methylmercury is released. So you're getting nutrients that stimulate algal growth being released when this is red, and then suddenly, a week later, it all mixes, so all those nutrients taken up to the top where there's light, algae can grow, and especially these harmful algal blooms there. So this is something that, or I guess this is showing this, it's called internal loading. We get phosphorus, we get methyl mercury, and we get algal blooms and fish kills, things like that. So using computer modeling of Clear Lake, we've actually come up with a design sizing of a hypolimnetic oxygenation system. What a beautiful name. It just rolls off the tongue. Hypolimnetic oxygenation. What is this? The hypolimnion is the bottom of the lake. Fancy word limnologists use to confuse the rest of the world. So this is the hypolimnion. This is where the oxygen would be lost. This is the deep part of any lake. The problem is we're running out of oxygen. The solution is, well, add oxygen. It's not that hard, is it? It isn't. So basically what you do is run a pipe into the lake. You have a diffuser where very fine oxygen bubbles come out. You have to have an oxygen supply, and that keeps oxygen high, cuts off internal nutrients, cuts off mercury. This is what it would look like at Clear Lake. We're just doing an experiment in one arm, and this is where there's about 2 kilometers of diffusers. It's a big system, but it's an example of where modeling can be used in another lake. A model that was developed, tested, proven at Lake Tahoe is now being used in a very different lake, very close, relatively close to home. Second example, and this I'm pretty much going to stop here. Yeah, when I retired, I gave up many of the projects I had. I just, you take this one, you take that one, you do that. But there are a couple I kept to myself. This is one. Nobody gets to touch this one except me. So this is lakes of Patagonia in Chile. So these are beautiful lakes. So the Andes Mountains, volcanoes, glaciers. You think you're in the high Sierra there, except this lake is at about 200 feet above sea level. So it's a very temperate lake. Chile has a different problem than Clear Lake. It actually, believe it or not, it has the same problem as Tahoe, but 50 years later. The south of Chile, Patagonia, is where people are moving to now because places like Santiago are becoming increasingly unlivable. So they have what we had here in the 60s and 70s, growth and population growth and development in the Tahoe Basin is starting to happen in Patagonia. And so we started this alliance with a group down there, formed a nonprofit. And the idea is to, again, use models and use the experiences that we have, the experiences the League to Save Lake Tahoe have, even the land development policies enacted by the TRPA. All of that is being looked at to say, how can that be used to maybe manage things better than we did here over 50 years ago. But one of the interesting things, so that's one particular lake. We're working on 14 lakes. Again, we can't afford to monitor them all. This one we did monitor. This is called Lake Yanquihue. It's almost identical to Lake Tahoe. It's not quite as deep, but it's just a tiny bit bigger area-wise. This is its watershed, black dotted line. So like Tahoe, it's a small watershed compared to the size of the lake. This is where it's located. So just to touch on one thing. So these are two sets of graphs. So, and these are model results. So we did measurements there. We used the same model. We calibrated it, confirmed that we're happy that it represents what's happening. The black line on both those graphs represents the surface water temperature in 2021, 2022. One of the things we're interested there is what's the combined effect of development and climate change? And that's what we were worried about. This dashed line represents the same temperature over the year, but this is using projected climate change for pretty much 70 years from now, assuming very little decrease in the rate of carbon emission to the atmosphere. What you can see, the difference between the dashed lines in both graphs is really small. We run this for Tahoe, there's a big difference. You run it for most lakes in the world, there's a big difference. And 70 years in the future, they're all warmer. This lake, this is showing it's actually getting cooler in the early part of the year. So this literally blew us away. How can climate change not have an effect on this lake? If you go back to this image, the reason we think is South America gets pretty narrow. There isn't much land in the southern hemisphere. So in a way, the Southern Ocean, Pacific Ocean, Southern Atlantic Ocean, buffer climate change. I mean, climate change is happening, don't get me wrong, but its impact on lakes in this southern part of South America is muted because of climate change. So this is an example of where the modeling's actually teaching us something. It's, when you think about it, oh, yeah, that does make sense. But without having these projections, we may not have come to that. So at this point, I'm going to stop. I don't know how much time we have left.
3 minutes for questions.
Oh, man. I'm sorry. But I'm sure that's all you wanted to know about Tahoe and other places. Yeah. So, any questions? What did you really want to know? Okay. In 3 words, I don't know. But in order for particles, whatever their origin, to have an impact on clarity, they have to be in a particular size range, and that's about 1 to 6 microns, because it's the interference with light, visible light, that changes the clarity. So the microplastics work we've done, the microplastics work that other people have done, have all focused on, well, literally macroplastics. It's a very coarse net. I'm just trying to think. I think most of the net we have has a mesh size of 100 microns. So and everybody else has been collecting 100 micron plus plastics. So we know there are lots of plastics. We don't know how many are in that critical size range. And those smaller ones are the ones that will have health effects on us and on wildlife. So that's a really hot question now, not just here, everywhere. Yep. On the clarity, how reliable is that? Okay, the person who was responsible for collecting the data in the 60s is at the back of the room. So I have to say that was impeccable data. If only we could do half as well today, we'd be doing fine. But actually, I mean, much of the data that was taken then was, again, with a Secchi disk, which seems like a child's toy. I mean, it seems really simplistic. Scientists have all this fancy equipment, and we're using this plastic disc. But it's remarkably reliable and repeatable and understandable. And back in that day and today, we're using other instruments to measure different parts of the light spectrum, and nothing says that that Secchi depth data was wrong. So it hasn't changed. I mean, every year, that long-term Secchi depth data, every year, every month, people would say, how do you know that's not the eyesight of the observer? Well, we've checked that, and it isn't. So that it's real. And I think that's one of TERC's greatest assets is we have literally a half century or more of data that most lakes don't have. Yeah.
I'll ask a question. When you talk about your average Secchi disk depths, how frequently are they measurements taken? Are they near shore, deep water, and is it done year round?
Taken about every 10 days, year round. They're all in deep water. 2 stations, one's in about 125 meters of water. The other one's pretty much at the deepest point of the lake. And the statistical differences between those 2 stations are very small. This new instrument I mentioned, this wire walker, the one that walks down the wire with wave energy and comes up, that's going to be measuring up to 20 meters every 20 minutes. It's not going to have a Secchi disk on it, but it's going to have instruments that measure how much light is penetrating down. And so for the first time, we'll be able to see sort of continuously how much the clarity, the equivalent Secchi depth, is changing between these 10-minute periods. I mean, you can't take a Secchi depth measurement at night, but you can still measure water clarity at night. So again, we'll get a sense of these processes, these things that we haven't been able to measure before. But I mean, most scientists don't look for ways to say, our data is great before they've gone through and looked for flaws in their data. What's wrong? Is there some systematic error that we've made? And we've done that multiple times. I even had a graduate student one time who was not convinced. He thought maybe there's an effect of the time of day the measurement is taken, because the sun is lower in the sky at 2 o'clock. And so he basically could make corrections for the sun angle, and it turned out it was of no impact. We generally take the measurements between plus or minus 2 hours of when the sun is at its highest point. And if we take one late in the day, we usually disregard it. We don't include it in the annual average. So those are data that we really fully trust. Yeah.
Water was so warm.
Yeah. Oh. Oh, good. Well, you're welcome. I'm not director anymore, so I can't make that happen again, but I put in a request to the right person. Well, yes.
Wondering if
Oh, okay. This is guilty. Actually, we're just in the process of doing some final changes to the paper we're about to submit on that. So this happened just in Emerald Bay, not in Lake Tahoe. It turns out, it seems that based on data taken through the 60s, the mysis shrimp are an introduced shrimp. They're introduced deliberately to many lakes across the West as a way of potentially increasing fish size. And it was a terrible decision, but we're all stuck with the consequences of that. So in Emerald Bay, in I think 2011, in Tahoe, the mysis shrimp have a 4-year life cycle. And Emerald Bay is a 1-year life cycle. I don't know why. It doesn't matter. In Emerald Bay, we went down one time and to measure mysis shrimp, there were none. They went out, go with the way you measure them, you go out at night because they come up to the surface, you put the net down to the bottom, you draw it up. Normally in Tahoe and Emerald Bay, you get something like the equivalent of 100 or 200 mysis shrimp in that net. So on this particular night, 0. Like, whoa, ain't that strange? So don't worry, go out again in 3 months, do the same thing again, maybe 1. I mean, it was like nothing. It had never been observed before. And so every 3 months they kept doing that, no shrimp. What they did see was the return of a zooplankton that had been decimated when the mysis were introduced back in the 60s. It's called Daphnia. And Daphnia is known to be sort of always acquainted with very clean, clear, pristine waters. I mean, they're really good at filtering out the water. So suddenly you've got no mysis, the return of large numbers of Daphnia, this shrimp, this zooplankton, and at the same time, the Secchi depth increased. I gotta try to remember the numbers now. From something, I mean, Emerald Bay is not as clear as Tahoe. So let's say from about 10 meters of Secchi depth to 20 meters of Secchi depth in something like a 2-year period. A 10-meter increase that has not been seen anywhere in this system, ever, despite millions, tens of millions of dollars being spent. Move along a couple of years, the mysis come back, the Daphnia get eaten, and the Secchi depth goes back to where it was. And so that was something like a 5-year set of observations over most of it 3 monthly, but then we had a period of more intense monitoring. So it remains somewhat, people have different opinions on what happened. I am of the belief that in a way, because mysis were introduced in the 60s, at the same time, lots of other changes were happening here, that their impact possibly wasn't fully appreciated at the time. It was the watershed changes, the development we were focused on. Both, I think, were important. And so now if we can, there's some ideas we have to take that further. We had some ideas on even using Emerald Bay, I mean, they're back in Emerald Bay now, is to harvest them and actually do a deliberate experiment. Why, your real question, why did they disappear? We don't know, but we think it may have been a reproductive failure of some sort. Reproductive failure, they have a 1-year lifespan, 99% of them get wiped out, but eventually they're going to come back. The connection between Tahoe and Emerald Bay is very small, so it's not as if they got an influx of mysis from the main lake. Yeah. Oh, well, it depends who you ask. Some say the fishing's great, and others say it's diminishing. The same with crawdads. Some people see more, some more. Sorry? Well, yeah, so the meadows are important because they were a great place. Yeah, most, there are a few. Yeah, but I mean, they were great nurseries for small fish. Getting back to the Daphnia, a great food for fish. And so you have, their changes are happening. You also had the introduction earlier than that of the Mackinaw, which are very voracious predators. Demise of the Lahontan led to the introduction of the Mackinaw. So there have been huge food web changes, huge land changes. I mean, okay, this is anecdotal. So around the time this was happening in Emerald Bay, the whole mysis demise, we were talking with the fishing guides. That's South Shore. Are you seeing anything? So the state record for a kokanee was set in about, I think, 1971, and soon after the introduction of mices. And since then, they've all gotten smaller and smaller. In, I think it's 2014, a few years after the mysis disappeared, the Daphnia came back, a new state record for kokanee was set with a fish caught pretty much at the entrance to Emerald Bay. Again, anecdotal, but that's, and you know, there are photographs of the fish they were catching at that time, but then that time has passed. You know, the trick will be to, can we reproduce that? Can we sustain it? Can we manage it? And actually, mysis are easy to catch. So how am I doing? So they spend most of their lives at the bottom of the lake. They don't like light. So they come up at night and they occupy a thin band, a band just 10 feet wide. And when they're there, they're eating all the things the fish would normally like to eat. So they're essentially, instead of increasing the fish population, they've removed their food source. And then when the sun comes up, they go back down. So if you go out at night when they're in a narrow band, you can see with an echo sounder, you can see where they are. You basically be able to troll for them in a very thin band. If you wait till the daytime and at the bottom, you'd be disturbing the bottom. You don't want to do that. So it could be a relatively straightforward process. Will we ever get rid of them totally? No way. But you know, some of the early work indicated if they're down to a value below about 23 per square meter, we're currently about 100, 150. If they're at about 23, then they can coexist with things like Daphnia. And to me, that would be an interesting management strategy. The what? Mosquito?
Mosquitoes are gone.
Are they?
No.
Oh, yeah, I've got some. I think it's my pond. Yeah, I don't do mosquitoes. I don't know, but yeah. So, I mean, I'm sure wetlands have mosquitoes would go with the wetlands, I would think, but there are still areas where there's localized ponds for months in the spring and summer. I'm not seeing birds this spring. I'm up at 7,000 feet and we get very few birds right now. I don't know where they've gone. I don't know what everybody else is seeing.